Hello everyone. Today we'll be presenting our project titled Divide and Conquer, comparing centralized and distributed architectures in large language models. I am Arsh Desai and I am joined by my teammates NVJK Karthik, Priyesh Gupta, Vinayak and Vivan Sharma. So our project basically deals with LLMs. They have emerged as a transformative force and reshaped the whole landscape of language technology with their remarkable capabilities. However, as these models continue to grow in size and complexity, the architectural decisions underpinning their deployment becomes increasingly critical as hosting and deploying these complex LLMs on low-end hardware devices becomes a very big issue. The traditional centralized architectures, where the LLMs are hosted on a single device, will always face scalability challenges due to their computational expensiveness, and this will threaten to limit the full potential of LLMs. Then let's come to the distributed architectures. In contrast to the centralized architecture, the distributed architecture offer a very promising alternative. They harness the collective power of multiple computers to host and serve these massive models. The distributed architecture helps in overcoming the scalability challenges by providing the required computational power as well as the required amount of memory, as in the RAM, which enables the complete utilization of sophisticated model capabilities. But while we discuss the benefits of distributed architectures, we must also discuss some of the drawbacks, such as the network bandwidth overheads and synchronization issues among the nodes which host the model. We also need to tackle some of the misconceptions that exist within the global community when we talk about distributing a neural network across multiple devices. So, what we have done is we have used Microsoft's open source framework called Petals to distribute Meta's cutting edge LLM Llama 3, which has only been released a few days ago, and this is how it works.
To tackle the task of hosting massive LLMs on a distributed network, we leverage the power of Petals, a framework that is designed specifically for distributed machine learning workloads. Now let us talk about how does it work. Participants can run server, client or both roles. Servers host subsets of the model layers on their GPUs. Clients form chains of servers to handle inference or fine-tuning. Let's walk through how the inference process works with Petals. The client stores the token embeddings locally, a small fraction of the total model parameters. The client finds an available chain of servers that collectively hold all the model layers. The client sends the token embeddings to the first server in the chain. Then each server computes activations for its layers and passes them to the next server. The final server returns the representations back to the client. Then the client can then compute the next token probabilities based on these final representations. Beyond just inference, Petals also enables collaborative fine-tuning of large language modelings in a distributed manner. Clients own the trainable parameters like adapters or soft prompts. Servers host the original pre-trained model layers. Servers compute and pass activations but don't store trainable parameters. During the forward pass for fine-tuning, the client routes batches of training data through an available server chain. Server compute activations for their layers and pass to the next server. Then the client obtains representations from the final server, and then the client's local classification head generates predictions.
Now in the next step, the backward pass then works as follows. The client computes gradients for its local trainable parameters. It then sends the activation backwards through the same server chain. Each server then computes gradients with respect to its activation it produced. Then the server returns these gradients back to the client. The client then uses all the gradients to update its local parameters. This distributed training approach enables clients to effectively fine-tune the large models without storing the full model locally while parallelizing compute across available servers, allowing seamless scaling to extreme large models. By decoupling the training of small sets of parameters from the pre-trained model itself, Petals makes it feasible to continuously adapt massive large language models. Now we'll talk about the setup that we had used. To put up the distributed capabilities of Petals to the test, we set up a private network with fairly modest hardware, that is. One was the MacBook Air, and the two laptops were equipped with the hardware of NVIDIA GTX 1650, and one laptop was an NVIDIA RTX 3060. These four laptops were connected together in a private swarm, forming our distributed petals network. The large language module were aimed to host on this network was recently released Llama 3 8 billion parameters from Meta, which is a new state-of-the-art open source large language model which was released on 18th of April.
Now, let's talk about the benchmarking. As large language models continue advancing, we need more robust benchmarks to evaluate their capabilities. We need to test models' world knowledge and reasoning skills as well. MMLU or Massive Multitask Language Understanding benchmarks aim to fill the gap. It comprises a diverse set of 57 tasks spanning multiple domains like mathematics, history, science, law, and more. Crucially, MMLU evaluates models exclusively in zero-shot and few-shot settings, where they must rely solely on their pre-existing knowledge without any task-specific training data. This approach more closely mirrors how humans apply their learned knowledge to niche situations, making MMLU a challenging yet meaningful measure of LLM's world understanding and problem-solving prowess. The MMLU benchmark results provide valuable insights into the performance of state-of-the-art large language models across a wide range of challenging tasks. Among the centralized models evaluated by Meta, the Llama 3 8 billion model achieved the highest score of 67.4%, closely followed by the Llama 65B at 63.4% and Llama 2 34 billion at 62.6%. Our distributed implementation of Llama 3 8 billion model utilized the Petals framework, attained a competitive score of 60.4% on the MMLU benchmark. While lower than the centralized Llama 3 8 billion model published result, our score outperformed several other state-of-the-art models, including the Mistral 7B at 60.1%, Quen 7B at 56.7%, and Llama 2B family of the models, with the 13B variant scoring 54.8% and the 7B variant scoring 48.3%.
As we look towards the future of distributed architectures for large language models, there are several promising avenues for optimization and exploration. One key area is enhancing communication protocols and load balancing algorithms to minimize overhead and bottlenecks in the parallelized model execution across the distributed cluster. Advanced protocols and dynamic request routing mechanisms can significantly improve efficiency. Additionally, integrating heterogeneous hardware accelerators like FPGA and ASIC into the distributed infrastructure presents an opportunity to leverage specialized architectures optimized for efficient tensor operations. This hybrid approach, combining varying computational capabilities, could further boost performance. Exploring edge computing paradigms is another intriguing direction, aiming to minimize latency and bandwidth constraints often faced in centralized cloud systems. By bringing LLM capabilities closer to data sources and end users through edge deployments, we can enable a wider range of latency sensitive applications. Moreover, current implementation primarily focus on model parallelism for single inference request. Investigating architectures that enable efficient batch inference can help leverage the full parallel computing power of hardware accelerators like GPUs and TPUs, enhancing throughput. From the results of the study, we can say that architectural design decisions are critical in the context of large language models, as they have a significant influence on scalability, performance, and resource consumption. Distributed architectures stand out amongst these architectural factors as a strong substitute, providing LLM deployment options that are accessible, affordable, and energy efficient. The results of study on distributed architectures make a substantial contribution to the current discussion about LLM development. Additionally, they provide practitioners and researchers with invaluable guidance, enabling them to make well-informed decisions that will influence the direction language model technology takes place in the future. Through the utilization of distributed architectures, researchers facilitate the progress of language model deployment and utilization, guaranteeing a more promising and long-lasting future for LLM development. So, we would like to acknowledge the contribution of Dr. Animesh Chaturvedi sir, who guided us in designing and executing this project. And these are the details of our team. Thank you for listening to this presentation.